Alright, so last time we derived the Rodrigues formula, and on this slide you see a list of 4 exercises on the Legendre polynomial. I indicated that the Legendre polynomial has exactly n distinct roots. Pnx has exactly n distinct roots in the interval -1, 1. And I also told you that these roots were used by Gauss in 1814 for developing his quadrature formula, what is today known as a Gaussian quadrature, which gives the best possible error estimate among all quadrature formulas. The Gaussian quadrature has the least error. So, because of this, we shall now give a detailed proof that the nth Legendre polynomial has n distinct roots in the open interval -1, 1. We shall not discuss the Gaussian quadrature, but I shall give a reference to S. Chandrasekhar's book on radiative transfer that you see on the slide. Okay, so we will need again and again the Rodrigues formula, namely Pnx equal to 1 upon 2 to the power n, n factorial, nth derivative of x squared minus 1 to the power n. Now, of course, since we are interested in the roots of Pnx, we can ignore this constant factor 1 upon 2 to the power n into n factorial. So, we will ignore this constant factor and we shall concentrate on the polynomial nth derivative of x squared minus 1 to the power n, and we shall show that this polynomial has n distinct real roots in the interval -1, 1. Alright, so let us begin. So, first let us take a few minutes to discuss the Rolle's theorem. What does the Rolle's theorem say? It says in particular that if f is a polynomial which vanishes at 2 points a and b, then the derivative must vanish at least once in the open interval a b. This is the classical Rolle's theorem that you study in your 12th standard level. Alright, so now let us assume that the polynomial f not only has a root at a and b, it has a double root at a and a double root at b. What does it mean to say that a polynomial has a double root at a? It means f of a is 0, f prime of a is 0. It has a double root at b as well, so f of b is 0, f prime of b is 0. So, we got that on the display in the slide. So, now let us apply Rolle's theorem, and we know that there is a c in the open interval a b such that f prime of c is 0. But now we have that f prime, the derivative, vanishes at 3 points, namely at a, c and b. So, we can apply Rolle's theorem to f prime, and we conclude that f double prime must have at least one root in the open interval AC and one root in the open interval CB. So, now we know that f double prime has 2 distinct roots in the open interval AB, because these intervals AC and CB are disjoint intervals, and on each one of them f double prime has a root. So, f double prime has at least 2 distinct roots in the open interval AB. So, after this generality, let us apply this idea to this function f of x equal to 1 minus x squared the whole squared. So, we apply it to 1 minus x squared the whole squared. Observe that this has a double root at -1 and a double root at 1. So, by what we have just shown, f double prime, the second derivative of 1 minus x squared the whole squared, must have 2 distinct roots in the open interval -1, 1. But the second derivative of a 4th degree polynomial is a quadratic polynomial, and a quadratic polynomial anyway cannot have more than 2 roots. So, this particular polynomial, the second derivative of 1 minus x squared the whole squared, has 2 distinct roots in the open interval -1, 1, and these are all the roots. So, P2 of x has exactly 2 distinct roots in -1, 1. Okay, the idea can be carried over to the next level. Now, suppose f is a polynomial with a triple root at a and a triple root at b, then the third derivative must have at least 3 distinct roots in the open interval a b. Apply the same idea again, f of a is 0, f of b is 0. So, by Rolle's theorem, f prime c must be 0 for some c in the open interval. So, now a is a triple root. So, f prime of a is 0 and f prime of b is 0. So, now f prime is 0 at a, c and b. So f double prime is 0 at say alpha and f double prime is 0 at say beta, two distinct points alpha and beta. But now we know that f double prime is also 0 at a and b because a and b are triple roots. So now f double prime vanishes at a, alpha, beta and b. So we got three disjoint intervals a alpha, alpha beta, beta b. Each of these disjoint intervals must contain a root of f triple prime. So f triple prime has at least three distinct roots in the interval AB. So let us apply this to 1 minus x squared whole cube. 1 minus x squared the whole cube has a triple root at minus 1 and a triple root at 1. So the third derivative must have three distinct roots in the open interval minus 1, 1. In other words, the third Legendre polynomial must have at least three distinct roots, but being a third degree polynomial, it cannot have more than three roots anyway. So we conclude that P3 of x has exactly three real roots in the interval minus 1, 1. Generally, we show that Pnx has exactly n distinct roots in the interval minus 1, 1. That completes the proof of the exercise that I had given. Owing to its supreme importance, I decided to give a complete proof of this. All right. We know that the Legendre polynomials form an orthogonal system of polynomials on the interval minus 1, 1. So whenever we have a vector space V and an orthogonal system of vectors v1, v2, vn, then we would like to find the length of these vectors v1, v2, vn, etc. so that we can divide by this length and we can get an orthonormal system. From an orthogonal system, we should be able to pass on to an orthonormal system of vectors. So in other words, we have to find the norm squared of each of these vectors. So what are the vectors here? Pnx. So what is the norm squared? Inner product Pnx with itself. So what is the inner product of Pnx with itself? Integral minus 1 to 1 Pnx the whole squared dx. But remember, there is a 1 upon 2 to the power n n factorial. So let's multiply by 4 to the power n n factorial squared just to clear the fractions. And the right hand side becomes integral minus 1 to 1 nth derivative of x squared minus 1 to the power n the whole squared, which I have written it as n dn x squared minus 1 to the power n product with dn x squared minus 1 to the power n dx, where the d stands of course for the derivative and the dn stands for the nth derivative. So now we must repeatedly integrate by parts and transfer all the derivatives from the second factor onto the first factor. You may recall that we already done this exercise to prove the orthogonality of these polynomials. We will repeat the same idea. And now, so first let us perform the integration by parts once. So one integration by part will transfer one derivative from the second factor onto the first factor. We get 4 to the power n n factorial squared integral minus 1 to 1 Pnx squared dx equals minus integral minus 1 to 1 d to the n plus 1 x squared minus 1 to the power n d to the n minus 1 x squared minus 1 to the power n dx plus boundary terms. These boundary terms have been indicated by B1 in the last displayed equation in the slide. So we must now examine what these boundary terms are. So what are the boundary terms? When you integrate by parts, integral u dv by dx will be minus integral v du by dx plus the boundary terms. What are the boundary terms? uv at b minus uv at a. So let us calculate these boundary terms. So b1, which is nth derivative of x squared minus 1 to the power n, n minus 1 derivatives of x squared minus 1 to the power n at minus 1 and 1. But notice that x squared minus 1 to the power n has plus minus 1 as roots of multiplicity n. So all derivatives of f up to and including order n minus 1 must vanish at plus 1 and minus 1, which implies that the boundary term b1 must be 0. because a boundary term is exactly nth derivative of x squared minus 1 to the power n minus 1 derivatives of x squared minus 1 to the power n, and at minus 1 and 1 the second factor vanishes because plus 1 and minus 1 are n-fold roots. And now that the boundary term vanishes, we will perform one more integration by parts. One more derivative shifts to the left hand side, and then what we get? We will get 4 to the power n factorial squared integral minus 1 to 1 Pnx the whole squared dx equals integral minus 1 to 1 d to the n plus 2 x squared minus 1 to the power n d to the n minus 1 x squared minus 1 to the power n dx plus b2, where the boundary terms of b2 are d to the n plus 1 x squared minus 1 to the power n d to the power n minus 2 x squared minus 1 to the power n evaluated at minus 1 and at plus 1 and at the difference. And again, as I explained, this must be 0 because plus 1 and minus 1 are n-fold roots. So, the n minus second derivative of x squared minus 1 to the power n must vanish at both these endpoints. And we carry on further and further. After integration by parts n times, we get 4 to the power n factorial squared integral minus 1 to 1 Pnx the whole squared dx equals minus 1 to the power n integral from minus 1 to 1 d to the 2n x squared minus 1 to the power n x squared minus 1 whole to the power n dx. Observe that d to the 2n x squared minus 1 to the n equals d to the 2n into x to the power 2n, because all the other terms will become 0 when you differentiate 2n times, and so it will be simply 2n factorial, whereby 4 to the power n into n factorial squared integral minus 1 to 1 Pnx the whole squared dx equal to 2n factorial integral from minus 1 to 1 minus x squared raised to the power n dx. Remember, I have a minus 1 to the power n outside the integral that was gobbled up by x squared minus 1 to the power n, and you get 1 minus x squared to the power n. Okay, now since the integrand is an even function, it will be twice 2n factorial integral from 0 to 1 minus x squared raised to the power n dx. Now make the substitution x squared equal to u, and we get 2n factorial integral 0 to 1 minus u to the power n u to the power minus half du. Now this last integral is something that you should recognize, and what is it? It is the beta function. What is the beta function? Beta pq equals integral 0 to 1 minus u to the power p minus 1 u to the power q minus 1 du, where p and q are positive numbers. Beta function is symmetric. Beta pq is the same as beta qp. You have studied the beta function in your elementary courses, and you need to recall the definition of the beta function. So the expression that we have obtained can be written as 4 to the power n factorial squared integral minus 1 to 1 Pnx the whole squared dx equals 2n factorial into beta of n plus 1 and half. Now we need to recall the famous beta gamma relationship of Euler. Beta pq is gamma p into gamma q upon gamma p plus q. So what happens? We get on the right hand side, we get 2n factorial into gamma n into gamma half upon gamma n plus 3 by 2. So what do you get? Gamma n plus 1 is n factorial, gamma half is root pi, and the denominator will be gamma n plus 3 by 2. All right. So 1 n factorial will cancel out from both sides, and what do we get? We will get the inner product integral Pnx the whole squared dx will be equal to 2n factorial upon 4 to the power n into n factorial into n plus half, n minus half, etc., and all the way up to 3 by 2 into 1 half. Gamma n plus 3 by 2 is n plus half gamma n plus half. Gamma n plus half is n minus half gamma n minus half. That's how repeatedly you keep using the recursion formula, gamma x plus 1 equal to x gamma x again and again and again. That's how you get this denominator. Of course, the 4 to the power n factorial has been brought to the right hand side. So now you need to simplify this. If you simplify this, you get the very simple formula that the L2 norm squared of the nth Legendre polynomial is 2 upon 2n plus 1. So the norm of Pn is square root of 2 upon 2n plus 1. So we have found the lengths of these vectors, and we can divide by the length if you wish, and we can get an orthonormal system of polynomials in L2 of minus 1, 1. Of course, we should check this out. When you derive this kind of formula, you must always verify the correctness for small values of n. Suppose if n is 0, what is P0? P0 is a constant polynomial, and norm P0 squared is 2, and that checks out. And when n equal to 1, what is P1 of x? P1 of x is x, and so you can quickly integrate x squared dx from minus 1 to 1, and you get 2 by 3, and again it checks out, and we just spot check the correctness of this formula. So we have derived the normalizing factor. So here are some more exercises on the Legendre polynomials. Prove that Pn prime 1 equal to 1/2 of n into n plus 1. Pn plus 1 prime minus x Pn prime is n plus 1 Pn. These two identities can be checked using the Rodrigues formula. So for example, to prove Pn prime of 1, what do? Remember the Rodrigues formula, 1 upon 2 to the power n factorial, nth derivative of x minus 1 to the power n into x plus 1 to the power n. You need to apply the Leibniz rule for nth derivative of a product of two functions. J derivatives will fall on the first factor, n minus j derivatives will fall on the second factor. But remember, after differentiating, you are going to put x equal to 1. You are calculating Pn prime of 1, right? So if you look at the factor x minus 1 to the power n, and if fewer than n derivatives fall in that factor, we will still have an x minus 1 factor left out, and that will become 0 when I put x equal to 1. So the only term that will survive is when all the derivatives fall on x minus 1 to the power n and no derivative falls on the other one. So that's what you will have to use to derive this formula. So I leave it to you to check this. The third formula can also be derived using the Rodrigues formula. And try out these things. Look at the 10th exercise. Suppose x to the power n equal to summation j from 0 to n cj pjx, then find cj and find cn in particular. How do you do this problem? Multiply both sides by Pnx and integrate. So you will get by orthogonality integral minus 1 to 1 x to the power n Pnx equal to Cn times integral minus 1 to 1 Pnx the whole squared. We have just done in great detail the normalization. Integral minus 1 to 1 Pnx the whole squared is 2 upon 2n plus 1. So we get that. So you have to calculate now integral minus 1 to 1 x to the power n times Pnx. Again you will have to do an integration by parts, and you will have to carry it out completely. The idea is very similar to what we have done so far. I will leave it to you to check it out. Next comes the generating function for the Legendre polynomials. Remember that in the earlier modules we have found the generating function for the Bessel's function. In module 1 we derived the generating function, we derived the Schlumilch's formula. So you got the sequence of Bessel's functions j and x, where n runs from minus infinity to infinity, and we looked at summation t to the power n j n x. We got exponential of tx by 2 minus x upon 2t. That was Schlumilch's formula. What we have here is the generating function for the sequence of Legendre polynomials. Given a sequence an of real or complex numbers, the generating function is given by summation n from 0 to infinity an t to the power n. This is a formal power series. It may happen that it converges. In the case of Bessel, it did converge and we got a closed form expression. The same thing happens with the Legendre polynomials. The sequence of Legendre polynomials has generating function n from 0 to infinity t to the power n Pnx, and this series does converge and it gives you a closed form expression, namely 1 upon square root of 1 minus 2xt plus t squared. The expression that you see on the right hand side you recognize is a Newtonian potential, and the connection with potential theory stems from this formula. And for details, you must consult the book of A.S. Ramsay, Newtonian Attraction, Cambridge University Press, page number 131, or page number 121 to 134 of the classic treatise of Oliver Diamond Kellogg, Foundations of Potential Theory, Dover, New York, 1953. We will give a proof of this formula following Courant and Hilbert's, and there are several proofs of this theorem, and what I had chosen is from Courant and Hilbert's monumental treatise, Methods of Mathematical Physics, Volume 1. I'll only sketch the proof, the details can be worked out, it's not difficult. And what happens is that you look at this function v of xt equals 1 minus 2xt plus t squared to the power minus half. Now, you can think of t as a parameter, and if t is small, then t squared minus 2xt is small. If t squared minus 2xt is small, it will be less than 1 in absolute value, and I can apply the binomial series. And you can expand it, and you can collect the powers of t, and you are going to get a convergent series sigma n from 0 to infinity Rnx t to the power n. So, this function, this potential function can be expanded as a power series in t whose coefficients are polynomials in Rx, where the polynomial Rnx is a polynomial of degree exactly n. You can easily see this if you do the algebra and you write down the binomial series, you can see that Rnx is going to be a polynomial of degree exactly n. The question is to prove that these polynomials Rnx exactly coincide with the Legendre polynomials. So, now we know that the series converges for small values of t and for all values of x. So, what we must do is that we must multiply two of these, one with put t equal to u, put t equal to v, multiply them together and make a double series out of it. So, we get 1 upon square root of 1 minus 2xu plus u squared, 1 upon square root of 1 minus 2xv plus v squared equal to double series rjx, rkx, u to the power j, v to the power k. Integrate both sides with respect to x over the range minus 1, 1. And what happens is, we get the left hand side integral. The integral on the left hand side can actually be computed in closed form, and that is where a little work is required. It's an amusing integral, I leave it to you. 1 upon square root of uv log of 1 plus square root of uv upon 1 minus square root of uv equal to summation jk from 0 to infinity u to the power j v to the power k integral minus 1 to 1 rjx rkx dx. Now, expand the logarithm. We have a logarithmic series, log of 1 plus u equal to u minus u squared by 2 plus u cubed by 3, etc. So, the logarithmic term can be written as summation n from 0 to infinity 2 u to the power n v to the power n upon 2n plus 1, and you must compare the like terms on both sides, namely compare the coefficient of u to the power j v to the power k in the last two expressions, and we get that integral minus 1 to 1 rjx rkx equal to 0 if j is not equal to k, whereas if j equal to k we get minus 1 to 1 rjx the whole squared dx equal to 2 upon 2j plus 1. Now, we must recall the fundamental orthogonality lemma which we proved to derive the Rodrigues formula. The same argument will now tell you that the rjx and the pjx must be identical for every j, and that completes the proof. Please look at this sketch and try to flesh out the details, and we shall stop here.